Zone. We're going to be doing another video version of our notes this week, and this week we're focusing on probability and heredity. Please make sure you have a piece of Cornell note paper in front of you, and in the topics section you're going to put probability and heredity. Next, we need to fill in the essential question, and for the purposes of these notes we're actually going to have 3 essential questions. The first essential question is, dun, 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 what is probability and how does it help explain the results of genetic crosses? The second one is, what is meant by genotype and phenotype? So what's the difference between those weird words? And the last one is, what is codominance? I know that's a lot of essential questions to have in that little space, so if you have to go into the notes section at the top, that's fine. Also, I want to remind you that because this is video notes, you can pause to either catch up to what I'm writing down or what's being presented on the screen, but you can also pause it if you have a question. And then you can write the question down in that section on the left-hand side of your Cornell notes. And I strongly encourage you to do so. So if something seems unclear to you, mark it down as soon as it seems unclear. And then when we go over it as a class, you can ask those questions and hopefully we can get everything cleared up for you. Okay, so now for the notes. The first thing we're going to talk about is the principles of probability. So in your notes section, you need to write that down. Principles of probability. Okay, so let's define probability. Probability is a number, and that's important. It's a number that describes how likely it is that an event will occur. Please note that it does not tell what will occur, just what is expected to occur. So, for example, if you flip a coin in the air, there's a 50% chance that it's going to land heads up, and there's a 50% chance that it's going to land tails up. Okay, if you flip it once and you get a heads up, it doesn't mean that the next time you flip it's going to be tails. It's just what you would expect. If you flipped it 10 times in a row, you would expect about 5 times to be heads and 5 times to be tails, but that doesn't mean that's what's going to happen. So I've written this down. I've written this down for you, hopefully to illuminate that fact. Giving you a little example here. If you tossed a coin 20 times, you would expect to get 10 heads and 10 tails, but that is not necessarily what will happen. Based on probability, that's what you would expect, but it's not what will happen. You could end up with 12 heads and 8 tails, or 13 tails and 7 heads. Or, I guess if you are one of those people that just gets really lucky, you could end up with 20 heads in a row. It's not likely that it'll occur. It's more than 1 in a million chance that that will occur. But it doesn't mean that it can't happen. Stranger things have happened, right? So, to help you thinking about the coin toss, I have a little picture of a guy flipping a coin. You don't have to add this into your notes. I just think it's boring to just look at a blank piece of white paper with writing on it. I figured I'd add something a little colorful. Okay. What's important to think of when we're thinking about genetics or thinking about coin tosses is this idea of independence of events. Okay, independence of events. Now, what does that word mean? I'll give you an example using the coin toss again. When you toss a coin more than once, the results of one toss does not affect the results of the next toss. These events are independent of one another. So again, if you tossed a coin twice and the first time you tossed it up in the air, you got heads, it doesn't mean that the next toss is going to be tails because there's a 50-50 chance of getting heads or tails and you already got a heads, right? These coin tosses, that first toss has no impact on the next toss. Okay, so again, I'm harping on this, I guess, but I really want you to know this. Each time you toss a coin, there is a 1 in 2 or 50% chance that it will be heads and a 1 in 2 or 50% chance that it will be tails. I'm going to give you an example here. Again, I know I'm harping on it. I apologize, but I really want you to know this. If you toss a coin 3 times in a row and it comes up heads each time, what is the chance that the next toss will also be a head? I know myself, like sometimes I think, oh, well, I'm due for tails, right? I've already gotten 3 heads. I'm due for tails. Well, unfortunately, that's not how it works. The chance is simply 1 in 2 or 1/2 or 50%. That all means the same thing, just like any other toss of the coin. Same thing goes for genetics. So let's say based on your parents' genetic makeup, you have a 50% chance of ending up with blue eyes versus brown eyes. Well, let's say you get blue eyes. That doesn't mean the next sibling has will get the brown eyes, right? They still have the same chance. They still have a 50% chance of getting blue eyes versus brown eyes, right? What happened in the past will not affect the current toss or the current genetic cross, right? What happened in the past will not have any impact on what's happening currently if they're independent events. So let's talk a little bit more about how probability and genetics come into play. Okay, the first thing we're going to talk about is something we worked on a little bit on Friday. I know you read this section already, so hopefully you are beginning to understand what this term means, but we're going to talk about Punnett squares. A Punnett square is a chart that shows all the possible combinations of alleles that can result from a genetic cross. And if you look at all those possible combinations and you put them into a number format, you can figure out the probability of a certain outcome. Okay, so that's what geneticists use Punnett squares for. They use Punnett squares to show all the possible outcomes of a genetic cross and determine the probability of a particular outcome. So the example that I want to use for these notes is something that we looked at in our book, and we've talked about it quite a bit in class. So remember when Mendel did his experiments with pea plants? He took plants that were always tall and he crossed them with plants that were always short. And the result was that he got all plants that were tall who had both a tall allele and a short allele. Then he allowed those plants to self-pollinate, and he wanted to see what the outcome would be and what the probability of that cross would be. So remember, he's crossing a tall plant with a tall plant, each of which has both a tall allele and a short allele. So what you do when you make a Punnett square is that you separate out the 2 alleles, right, for each one. So this is one plant here and this is another plant here. And let's see what all the different combinations could be. The first one is that if you had this plant, if it donated a tall allele, and this plant also donated a tall allele, you would end up with a tall plant that has 2 tall alleles. Over here, if this plant donated a tall allele and this plant donated a short allele, you would still have a tall plant, but in this case, they have inherited both a tall allele and a short allele. And that goes for the same thing here. If this plant donated a tall allele and this plant donated a short allele, you would have a tall plant that has both a tall allele and a short allele. The only time a plant that results from this sort of cross would be short is that if it inherited 2 short alleles, one from each parent. So here, if the parent donates a short allele and this parent also donates a short allele, the plant will end up being short. As you can see, in 1, 2, 3 out of 4 times, the plant will probably be tall, and at 1 out of 4 times, the plant will probably be short. Okay. And I have that written down. In a genetic cross, the allele that each parent will pass on to its offspring is based on probability. Next, we're going to talk about the words phenotype and genotype, which are kind of funky little words. As you can see in science, they like to use words that will confuse you the most, right? Because it makes it fun for us teachers. Ha ha ha. Okay. First, we're going to define phenotype. An organism's phenotype is its physical appearance or visible traits. The way I like to remember what phenotype is, because there's so many vocabulary words to remember, is that phenotype begins with PH as does the word physical. So when you're talking about a phenotype, you're talking about what it looks like, okay? So in this case up here, the phenotype of this plant, and of this plant are that they are tall. The phenotype of this little plant over here will be short. And that's how, and we know that based on the genotype. So let's talk about what that is. An organism's genotype is its genetic makeup or allele combinations. So up here we have an organism, a pea plant, that has inherited 2 tall alleles. Its genotype is capital T, capital T. Its phenotype is that it's tall. This plant over here will have a genotype of capital T, short t, and its phenotype will be that it's also tall. But again, its genotype is the allele combination. So one big T, one little t. Its phenotype is that it's tall. Over here, we have a plant that has inherited 2 small t's, 2 short plant alleles, and its phenotype will be that it is short. Again, something that I haven't talked about either, I just want to remind you up here. Anytime you have an organism, if you're talking about writing a genotype and you have one dominant genotype and one recessive genotype, sorry. I apologize. Blah, blah, blah. Let me start again. If you have one dominant allele and one recessive allele, you're always going to write the dominant one here first. So if you look here and you look here, in both cases, the dominant one is written first and the recessive one is written second. Okay, so I just want to remind you that. You're never going to see the recessive one written first and the dominant one second. Just keep that in mind. Okay. And to really make this clear, I'm going to write this down here. For example, a pea plant that has a tall phenotype could have a genotype that is big T or big T small t. A pea plant that has a short phenotype will always have a genotype that is little t. Okay, and that goes for the case of any time you have a, if a recessive trait is showing, if an organism is showing the recessive phenotype, it means that their genotype is 2 of the recessive alleles. Going to put down this here because it applies to humans and maybe it'll help. In this case, talking about phenotype and genotype, if a person has blue eyes, it means that their, and that's their phenotype, is that they have blue eyes. Their genotype is little b. If somebody has the dominant phenotype of having brown eyes, their genotype could be big B, little b, or 2 big B's. Okay? And we're going to talk about, instead of just saying big B, little b, we're going to give you some vocab to help you talk about it a little bit more readily without having to get so tongue-tied, as Mrs. Sansone has a tendency to do. Okay. An organism that has 2 identical alleles for a trait is said to be homozygous for that trait. So, for example, the little b, this is homozygous recessive because they have 2 of the recessive alleles. Over here, this is homozygous, but now in this case it's dominant because they have the 2 dominant alleles. Okay, so to illustrate that again, in the case of stem height, both a tall plant with a big T genotype and a short plant with a little t genotype are homozygous for the trait of stem height. All right, but what if they have a hybrid? Well, an organism that has 2 different alleles for a trait is said to be heterozygous for that trait. Heterozygous. In the case of stem height, a plant with a big T, little t genotype is heterozygous for that trait. And I'm going to give you an example of something. But now, okay, so now I want to move on to what did I put that there for? I apologize. Okay. In some cases, instead of having a dominant and a recessive allele, some traits will be codominant. In some cases, traits are neither dominant nor recessive, and they're called codominant. It's that if an organism inherits one allele from one parent and another allele from another parent for a certain trait, if it's a trait that's codominant, then they will show both in their phenotype. So here is an example. This is like my favorite thing ever. Okay, my kids are my favorite thing ever, but still, it's pretty cute. Here are some heterozygotes. So in this case, the goats had both a parent that was an all-black goat and a parent that was an all-white goat. And because the trait of fur color or hair color for goats is a codominant trait, they're showing both the black phenotype and the white phenotype together. They're just allele uneven. Okay, I apologize for being a little punchy. I'm very tired, and I hope that you enjoyed these set of notes. If you have any questions, please, 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 please write them in the margin of your notes where it gives you space to write the questions, and we'll go over them in class. Guys, this stuff isn't easy. It's really, really complicated. I want to make sure that you understand it and that you understand it well. We'll be doing lots of practice in class, but still, again, you know, the good thing about having video notes is that you can go back through and not only listen to my lame jokes again, but you can hear the material again. And I'm one of those people, if I hear it, I get it. So I really would take advantage of that if you are an audio learner. If you're a visual learner, just watch the notes again. That can help you too. Anyway, I hope you enjoyed. Have a good day.